Hello, my name is Diesel Organish of Group 15. That includes me, Zane Deal, Camden Hansen, and Jared Glean. And today we're going to be talking about reducing 3D printing emissions. So just for some context, 3D printing is a process which creates a physical object from a digital model by adding layers of material, just one right atop the other. This could be plastics, metals, or even cement. So modern 3D printing has revolutionized industries by enabling rapid prototyping and the creation of highly customizable devices. However, the widespread adoption of 3D printers has raised concerns of environmental and human health impacts. So the project we're working on today focuses on designing a control system aimed at reducing the particle number concentration by at least 90% to ensure a safer and healthier working environment. So just some design parameters for this project. We looked at a typical 140 meter cubed makerspace with 10 3D printers. In this space, the particle number concentrations were found to reach up to 25,000 particles per cubic centimeter with a geometric mean diameter of 42 nanometers. This puts the particulate matter in a ultrafine particulate range, which can be very dangerous because smaller particles can penetrate deeper into the lungs, causing more significant and severe health impacts. These symptoms can start out with things like coughing, throat irritation, chest tightness, and shortness of breath, increasing in significance to risk of heart attacks, irregular heartbeat, and even stroke.
Water-based filtration was initially considered as a method for managing ultrafine particle emissions in a 3D printing makerspace. This method operates by passing air through water, where particles are captured through impaction and diffusion. Water filtration systems can remove particles efficiently, achieving up to a 90% reduction, particularly for ultrafine particles under 100 nanometers. These systems also offer advantages such as reduced clogging and waste, making them appealing for continuous use. However, the practical challenges of maintaining water filtration in a high-use environment became evident. The system requires regular water replacement and specialized drainage, which adds complexity and maintenance demands that could be difficult to manage in a busy makerspace. MERV, or Minimum Efficiency Reporting Value, is a system used to rate the effectiveness of air filters at trapping particles of various sizes. MERV filters are widely used in air filtration systems to capture particulate matter, including the fine particles emitted by 3D printers. Filters with higher MERV ratings, particularly those in the range of MERV 13 to 16, are highly effective at trapping ultrafine and submicron particles, which are common in 3D printing emissions. The filtration process involves drawing air containing particulate emissions into the system, where it passes through a series of filters, each designed to capture particles of specific sizes. The higher the MERV rating, the more capable the filter is at capturing smaller particles. As the air flows through these filters, the particles become trapped, reducing airborne particulate concentrations. The cleaned air, now with fewer particulates, is then expelled back into the environment. While MERV filters are relatively easy to install and require less maintenance compared to water-based filtration systems, they do necessitate regular replacement to maintain their effectiveness. They also face some limitations in environments with higher concentrations of particulates, as this is the case with a busy 3D printing space. Combining MERV filtration with local exhaust ventilation can further enhance performance by capturing emissions directly at the source.
All right, moving on to potential solution number 3, we have fume hoods. When these 3D printers are in use, they can, of course, release harmful particles, fumes, and gases into the air, some of which are carcinogenic. Using the fume hood, the contaminated air is drawn into the hood through the front opening, typically through a sash or a door, and in this hood, the system maintains a slightly negative pressure, which pulls the air from the room rather than leaking out. This negative pressure helps to contain the harmful emissions and prevents them from escaping back into the workplace. Once inside the hood, the airflow carries the contaminants towards the exhaust. This airflow is specifically controlled by the unit. It typically consists of roughly 80 to 120 feet per minute, and this just ensures that all the contaminants are going towards the hood and not back into the room. After capturing the contaminants, the air is directed either to a filtration system or vented outside. Many fume hoods use filters such as HEPA filters to filter out the particulates within the room. To ensure everything is functioning properly, fume hoods are equipped with airflow monitors. These monitors are able to track the airflow and alert users if it drops below safe levels, which could be an issue if a filter becomes clogged or if the fan malfunctions. In providing this real-time feedback, it helps ensure the safety of the workers within the room. In short, fume hoods are really vital for keeping the air clean with working with these 3D printers and can prove to be a good tool in achieving clean air.
The stakeholders impacted by the implementation of a fume hood in a 3D printing environment span several key groups, each with distinct priorities and concerns. First, the primary users, students, researchers, and makers are at the forefront. Their health and safety depend on effective air quality management, as prolonged exposure to ultrafine particles can lead to respiratory issues. A fume hood, by reducing airborne particulates, ensures a safer space without introducing complex waste management challenges. Second, facility managers and educators play a pivotal role. They are responsible for maintaining compliance with safety regulations and minimizing operational disruptions. The fume hood's efficiency and reduced maintenance requirements align with their need for practical, cost-effective solutions. Unlike filtration systems that generate solid or liquid waste, a fume hood simplifies waste management, easing their logistical burden. Third, regulatory bodies and environmental agencies are critical stakeholders. As air quality regulations continue to evolve, implementing a fume hood demonstrates proactive adherence to environmental standards. While exhaust emissions require oversight, they present fewer disposal challenges compared to solid waste, offering a more manageable compliance pathway. Finally, manufacturers and suppliers of 3D printing equipment have a vested interest. By incorporating fume hoods into their designs or offering them as accessories, they can meet growing market demands for sustainability and health-conscious innovation, enhancing their competitive edge. This broad spectrum of stakeholders underscores the importance of balancing safety, efficiency, and environmental responsibility in advancing 3D printing technology.
So, after carefully evaluating the previous options, we chose fume hoods as the optimal solution for managing our emissions from the 3D printers. There are a few key reasons why fume hood stands out to us. First, in terms of the environmental impact, water and MERV filtration systems produce solid or liquid waste that needs to be properly disposed of, which can be challenging to manage safely, especially in a company that is not used to environmental regulations. In contrast, a fume hood releases particulate matter into the atmosphere, and the exhaust air is way more easier to control and manage than solid waste, making it a more sustainable option overall. When it comes to energy efficiency, fume hoods also are more practical. They're more energy efficient to run compared to water pumps, which often require additional power for filtration and fluid circulation, and it makes the fume hoods more cost effective. Lastly, as an economic standpoint, there are fewer ongoing costs associated with fume hoods. With water filtration systems, there are added expenses for waste removal, energy consumption, and more frequent maintenance. Fume hood, on the other hand, offer a more simpler, more streamlined solution that reduces both waste-related and energy costs. Overall, considering environmental impact, energy use, and cost efficiency, fume hoods provide the most balanced solution and sustainable solution for managing 3D printer emissions. Alright, before we get into designing our fume hood system, we have to talk about our assumptions and given operating parameters. So for given values, we're given a room size of 140 cubic meters, 10 printers, a particle concentration of 25,000 particles per cubic centimeter, with a mean particle diameter of 42 nanometers, with a geometric standard deviation of 1.68. So our assumed design parameters that we took liberty in with this project is the width of a printer is 0.62 meters, the depth of the printer is 0.626 meters, and the height of the printer is 0.760. We chose a number of 5 fume hoods in total, and the width of the room is 5 meters, the length being 7 meters, and the height being 4 meters. This gives us a total room size of 140 cubic meters. And going back to our design of our printers, all of these design dimensions were taken from the Raise 3D Pro 3 printer as shown at the hyperlink at the bottom of this slide.
To model the removal of particles from the makerspace, we must first establish the fume hood's fan flow. The fan flow is based on the face velocity on the opening of the fume hood sash. So as you open the sash farther, the fan will need to increase its speed. The volume of air exhausted will be the summation of each fume hood's fan flow. The air changes per hour, or ACH, is the measure of how often clean air replaces the volume of a room. In a non-pressurized room, the clean air rate is equal to the volume of air exhausted. It is noteworthy that fume hoods require slightly negative pressure to make sure that all of the air gets exhausted, so the clean air rate will be less than the volume of air exhausted, slightly. As far as the removal efficiency is, it's slightly counterintuitive, where the concentration of the upstream air is actually equivalent of the concentration of the exhausted air, and downstream is the concentration of clean air. This is because the original model of removal efficiency is based more on filtration or some other kind of removal, whereas in our case with the fume hood, we're relying on the dilution of the atmosphere. The removal efficiency of our fume hood is based on the upstream concentration, which is going to be equivalent to the exhaust air, and the downstream concentration, which will be the equivalent of air entering the fume hood. This is a little counterintuitive to most mass balances detailing a filtration model, where particles go through a filter and are removed from the airspace. In our case, we're exhausting air from the fume hood into the atmosphere. Assuming that we exhaust the air in an appropriate way, it will be well mixed and diluted enough to be negligible. So when the air comes back through the building's HVAC system, the concentration downstream will be equivalent to the average amount of clean air, which for ultrafine particles is equivalent to about 2,610 particles per cubic centimeter. We're also using an assumed emission rate for each 3D printer, with about 2 × 10⁻¹0 particles per minute per printer. With 2 printers in one fume hood, that's equivalent to about 4 × 10⁻10. As a result, we see an inverse relationship between the opening sash in the fume hood and the removal efficiency. This is because as you open the sash further, you'll need a higher fan flow. The fan will be working harder to remove air from the space. Whereas if the fume hood was completely closed and the fan was able to operate at a negative pressure, all of the dirty air from the makerspace would be removed and there would be no concern about particulate concentrations. As the sash opens further, the fan will have to work harder to remove the same amount of particles from the space. If the sash was closed completely, the fan would be able to effortlessly remove these particles. So long as the methods of exhausting air are appropriate, the particles emitted from the makerspace should be diluted to safe levels into the atmosphere. This will allow those in the makerspace confident that the clean air intaked into the building will be free from particle concentrations. Those working inside the makerspace would also benefit from reduced ultrafine particle emissions, which includes decreased risk of respiratory issues, cardiovascular disease, and impacts on fetal development, as well as other severe health concerns. While fume hoods may have been an appropriate fix in this scenario, future makerspaces should include appropriate ventilation in the base building design, such as using pressurized rooms or other methods to safely remove particles from the space. Thanks for watching our presentation on the reduction of 3D printing emissions. If you have any comments, be sure to let us know. Thanks again.